Okay, so our final speaker of the day is Nadav Cohen. He comes to us all the way from down the street at IAS. He's a research scholar at the School of Mathematics and the Institute for Advanced Study. And part of the impetus for this workshop was an interest in Nadav's work and doing a reading of some of his one of his papers on using tensor analysis to study deep networks, which is a very original way of thinking about deep networks. So he's sort of an unwitting progenitor of this workshop, and so we're very glad to have him speak with us today.
Thanks a lot. Thanks for the introduction. It's all downhill from here. And thanks to all those that stayed. Because of my talk and not the food that comes afterwards. So, quick disclaimer, I will not be talking about the tensor analysis works right now. I'll be happy to talk about it on other occasions. You can have another workshop. What I'll talk about today is a new work on optimization that actually fits in very well with Andrew's talk a couple of hours ago. And the title of the work is On the Optimization of Deep Networks, Implicit Acceleration by Overparameterization. Credit to my co-authors, Sanjeev, that you heard this morning, and Elad Khazan. Okay, so the structure of the talk will be very original. I'm going to start with an intro, theoretical analysis, experiments, and then conclude. Deep learning, the fact that it's going to bring world peace, how important it is, you all know that, otherwise you wouldn't be here. And the people sitting in this room probably also believe that it's very important to understand what is deep learning, what is actually happening there. And perhaps the most fundamental question in the theory of deep learning is, why depth? What does depth give us? Right? And the conventional wisdom, which is, I would say, pretty extensively backed by theory, is that depth boosts the expressive power. Right? Depth allows us to represent much more compactly functions that we would otherwise need to pay a very expensive price in order to realize. Okay? Composing functions one on top of the other admits some kind of exponential efficiency. And this can be formulated, and it has been proven in various settings. Okay? What is also conventional wisdom is that this expressive gain comes at a price, and that is that optimization becomes more difficult. Okay? We heard in various talks today the difficulties that can come with non-convex optimization. When we optimize deep nets, there could be local minima, there could be saddle points, various things could happen, and this was not the case with convex analysis. Right? So this is also something that is kind of deeply rooted in the community's conventional wisdom these days, backed by various empirical studies. And what we argue in this work is that depth can actually accelerate optimization. It could be that depth not only helps with expressiveness, but it could also help you optimize faster, even though it's non-convex. Right? So that was the punchline. Can all go eat now? Okay, so the common approach to analyze optimization in deep learning is to characterize the landscapes. Right? Characterize, and in particular, the critical points, the local minima, or the saddles. And there's a pretty long line of works. This is just a small sample. We heard one today by Joan. And notice that this kind of approach, by definition, prefers convex objectives. Nothing is simpler than an objective with a single critical point, which is the global minima. Nothing is simpler than that if you view the problem through the lens of critical points. Okay? So if you want to argue in favor of depth, this approach is not going to do it. Okay? You have to consider the dynamics of the optimization algorithm. Okay? You have to consider the specific algorithm on the specific problem and see how it moves in parameter space. Okay? And we actually saw an example of realization of this approach by Andrew. And going along this path, an immediate hurdle arises, and that is that expressiveness can interfere with our study. Okay? We would like to show that deep networks can optimize faster than shallow ones, than linear models. If we just naively compare a deep network to a shallow one, and we see that the deep network reached a lower training loss, or optimized seemingly faster, it is not obvious whether this is a result of some inherent acceleration phenomenon, or it might be that the deep network is just able to fit the training data better. It might be that the shallow network is just not able to reach the same training loss. Okay? And to address this hurdle, what we do, in line with Andrew's analyses, is we focus on linear nets. Okay? With linear neural networks, when you add layers, you don't change anything on in terms of expressiveness. Okay? You don't gain anything. And so if linear nets, deeper linear nets, converge faster than shallow ones, this has to be an outcome of some favorable properties of depth for optimization. It can't be a result of an expressive gap. Right? And notice that with linear nets, when you kind of replace a linear model by a linear neural network, you essentially replace a matrix parameter by a product of matrices. Okay? So it's an overparameterization. Right? And what we're going to do now is consider a very, very simple case. It's going to be a warm-up, just an illustration, and from then we'll move to the theoretical analysis. This is the example. You see my cursor? Yes. Okay. So this is the example that Sanjeev showed. We're just going to get into a little bit more detail now. This is probably one of the simplest learning problems you can think of. And that's LP regression. We have ourselves a linear model, assigns a scalar label to a vector instance. Our parameter is the vector W. We sum over a training set, okay, instances and labels, x, y, in a training set S, and we minimize the LP loss. Okay, we have a linear prediction. This is the true label, and that's it. The gradient of this objective with respect to the parameter W looks like this. Not difficult to see. Okay. One line. And gradient descent, not surprisingly, looks like this. At time t plus 1, the parameter moves with respect to where it was at time t in the opposite direction of the gradient. And there is some learning rate here, eta. Right? Sorry. Now, consider the simplest form of overparameterization that you could imagine. We're going to replace the vector w by a vector w1 times a scalar w2. Right? We have not changed anything about the problem. Okay? These two parameters, w1 and w2, together represent a linear model. This is completely redundant. What we are going to see here, kind of informally and afterwards formally, is that this has a vast effect on the dynamics of gradient descent. And we've actually also seen examples of this by Andrew. Okay, so now the gradients look like this. This is the gradient with respect to W1. This is the gradient with respect to W2. Okay, so this is a vector, and here we have a scalar. Okay? Gradient descent now operates on both parameters concurrently. Okay? W1 moves in the direction opposite of its gradient. W2 moves in the direction that is opposite to its gradient. Okay? What we ask is, when we optimize W1 and W2 through gradient descent, what happens to the underlying model, the end-to-end model? Okay, the vector W, which is just equal to their product. How does that move in parameter space? Okay? And what we can show, it's pretty simple, is that assuming the learning rate is small, yeah, that's kind of an informal statement. We will formalize it as we go along. Assuming the learning rate is small and the parameters are initialized close to 0, okay? In this case, we can write the dynamics of the end-to-end model, W, t plus 1, just plug in definitions of gradient descent. Okay? And after a couple of lines that I skipped here, we get this kind of update rule. Okay? So Wt plus 1 is equal to to Wt minus some constant that varies over time, times the gradient, minus some linear combination whose coefficients also vary over time, times previous gradients. Okay? And that's for specific coefficients varying over time. But what you can see here is that the mere introduction of a single scalar turned gradient descent into some scheme that involves an adaptive learning rate, okay, this rho t here that changes over time, and some kind of a momentum. Okay? By no means does this mean that it is a good thing to do. It just emphasizes the vast effect that overparameterizing, the slightest overparameterization can have. Okay? And now, with this in mind, let's go ahead and be a little bit more formal. Okay? So, we are going to analyze deep linear networks. Our basic model is a depth n linear network. It just maps a vector x in a linear, applies a linear mapping that's composed of a sequence of matrices W1, W2, W3, and so forth until Wn. That's n layers. Wj is the weight matrix of layer j. Okay? And given these matrices, we define the end-to-end weight matrix. We denote that by We, and that's just the product, of W1 till Wn. Okay? So when I work with W1 to Wn, that's the linear neural network. Underlying is a simple linear model that just maps the input to an output in a linear way, and that is We here. Right? Given some loss over a linear model, it could be L2 loss, could be the hinge loss, cross-entropy loss, you name it, that immediately introduces an overparameterized loss. Okay? That's the loss that we get for the linear neural network. Okay? So its variables are W1 to Wn, and the loss is actually equal to taking the end-to-end mapping and plugging that into our original loss. Okay? The question we ask is a very simple one. This is kind of a generalization of what we asked before, and it is the following. How does the end-to-end matrix behave when we optimize the individual layer matrices through gradient descent? Right? We are taking a linear model, replacing it by a linear matrix, by a linear network, optimizing that with gradient descent, and asking how does the underlying linear model behave. Okay? So, gradient descent over the linear network, it looks like this. The weight matrix at layer j in time t plus 1 is equal to its value in time t, minus some learning rate times the gradient of the overparameterized loss with respect to Wj. Okay? That's simple gradient descent. And the first theorem that we prove, and this is an informal statement, I'll formalize it a little bit more in the next slide, is the following. Assuming that the learning rate is small, right, and that the weight matrices are initialized near 0, We, the end-to-end weight matrix, follows a certain update rule, which we call the end-to-end update rule. It's written right here. We are now going to parse it, just understand the syntax, and then go and take a series of steps to interpret this thing. Okay, so in this slide, your only objective is to understand what's written here. Okay, we'll get deeper insights into this as we go along. So what do we have here? Like, okay. Hear me? Yeah, okay, good. So this is the end-to-end matrix at time t plus 1. It's equal to its value at time t, minus a learning rate, times some expression. Let's ignore the left-hand side here and the right-hand side here, and also the summation, okay? We are left with normal gradient descent, okay? But we do have these matrices and the summation, okay? And what we see here is that the gradient undergoes some transformation, okay? It's multiplied by a matrix from the left and by a different matrix from the right, and then there is some summation. What are these matrices? Okay? This matrix on the left, that's We at the current time point, times its transpose. That's a PSD matrix. It is taken to some fractional power, okay? J minus 1 over n. On the right-hand side, we have a similar matrix, but it's different. It's not We transpose. It's the opposite order, We transpose We. And that is also a PSD matrix, and it is brought to a different fractional power. The power here depends on j, as well as the one here. And so we sum over j between 1 and n. Okay? This is not something that just came out of the blue. This is exactly how the end-to-end matrix behaves when you apply gradient descent to the linear network. Okay? And we're going to go ahead and take a series of steps to try and understand this thing. But for now, what we see is that overparameterization with a deep linear network gives rise to some update rule that we have a closed form expression for. Okay? Another thing that's important to notice here is that this update rule does not depend in any way on the intermediate dimensions in the linear network. Okay? There's no dependence. You see it here. It doesn't matter what the dimensions were in the series of matrices W1 to Wn. That means that with deep linear networks, in terms of optimization, the width of the network is insignificant. Okay? It's only the depth, as long as you maintain the expressiveness and not kind of, yeah.
Based on the previous slide,
That's a really good question. So the memory here is embedded into the location in parameter space. That's a really good question. Okay. And we'll see kind of, hopefully we'll get a better understanding of that as we go along. So now we have ourselves an end-to-end update rule. And let's go ahead and say a few words about how we prove this and on the way formalize our assumptions. Okay? So the assumption that the learning rate is small, formally what it means is that we analyze the discrete updates through differential equations. Okay? That's what it means. And the second assumption that the matrices weights are initialized to small values, actually the real assumption is a little bit weaker. The assumption is that this condition holds at initialization. Okay, so the weight matrix of layer j plus 1 transpose times the weight matrix of layer j plus 1, it's the same matrix, at initialization needs to be approximately equal to the weight matrix at layer j times its transpose. Okay, this happens when you initialize the matrices close to 0. It also happens when you initialize them to be identity, for example. And we're going to talk about that. But putting that aside, what we show is that if this condition holds at initialization, then it will continue to hold throughout the entire optimization. What this means is that the singular spaces of the matrices wj plus 1 and wj align. The right singular spaces of layer j plus 1 coincide with the left singular spaces of wj. Okay? And this can be used to simplify expressions like this, series of multiplications between weight matrices. And that allows us to explicitly derive the update rule that you saw before. Okay? But for now, maybe this is a little bit less important. What's important is the update rule that's written on the top here. Okay? Now there's a question. Cynics will say, okay, that's all nice, but you made assumptions here, and it's unclear to what extent they hold in practice. So we know that indeed in practice people use small learning rates and people initialize weights to be small, but it's only approximately so. It's unclear to what extent your analysis holds. And so what we do is evaluate this empirically. Okay, so what you can see here, we'll see more experiments as we go along. Just now, for now, what you can see here are 2-layer and 3-layer networks on 2 different objectives. This is an L2 regression task. This is an L4 regression task. Each network is compared to its equivalent analytically derived update rule. Okay? So we optimize a 3-layer network, for example, look at the objective, and then we go to a linear model, not work with a deep network at all, optimize that linear model with the end-to-end update rule. That corresponds to depth 3, to n equals 3. And we see how the objective behaves that way. And you can see that they align very well with one another. Okay? So this is kind of shows that at least in some settings, or in the standard ones, because we didn't do anything special here, so you use the exact same learning rates that people use in the types of initializations, default and TensorFlow, and it indeed aligns. Okay, so empirically this kind of supports the validity of our assumptions. Okay, so now having established the end-to-end update rule and kind of arguing that the assumptions made there are realistic, let's go ahead and try to understand it. Okay? What does this thing mean? This scary beast. Okay? So, pretty simple claim is the following. If you arrange the weight matrix, the end-to-end weight matrix, just arrange it as a vector and rewrite the update rule, it assumes the following form. The vectorization at time t plus 1 is equal to the vectorization at time t minus a learning rate times some matrix multiplied by the vectorization of the gradient. If I omit this matrix, I would get exactly gradient descent. Right? It's all buried in this matrix, the entire effect of depth. And this matrix is a PSD matrix, okay, meaning that there is a preconditioning going on here. Okay, that matrix stretches the gradient in non-negative amounts in different directions. And the matrix, its eigendirections, are formed from the left and right singular vectors of the end-to-end weight matrix. Okay? The PSD matrix depends on where we are in parameter space. Its eigendirections are formed by the singular vectors of the end-to-end weight matrix, and the corresponding eigenvalues are large if the singular vectors that generated that eigendirection have high values. Okay, so let's try to understand what this means. We are optimizing a matrix through this update rule, and we're arranging it as a vector. The update rule looks like this. This is just normal gradient descent with a preconditioning matrix. The preconditioning matrix varies throughout the optimization. It depends on where we are in parameter space. Okay? Our location in parameter space is a matrix. Go to that matrix, apply an SVD. We have singular vectors, left and right ones. These ones give rise, these singular vectors give rise to eigendirections in the preconditioning. And if these singular vectors, their presence in the matrix is strong, they correspond to high singular values, then the eigendirection of the preconditioning will be accompanied by a large eigenvalue. Okay? And so the optimization here stretches the gradient in directions that agree with our location in parameter space. Okay? Don't be scared if this is a little bit vague. In the next slide, it'll be more concrete. We'll consider a special case. But for now, notice that because we assume initialization is close to 0, then WE, the end-to-end weight matrix, it's not just our location in parameter space, it's our displacement throughout optimization. We started close to 0. WE, where we are right now, that's the displacement that we went through. And so that means that the overparameterization, giving rise to this end-to-end update rule, induces a certain preconditioning that promotes movement in directions that we have already taken. Okay, so if there's some direction that we've already went through, significant mileage, this optimization scheme, the implicit effect of depth, will encourage us to move faster in these directions. Yeah?
Is this somehow related to like...
It's very preconditioning is a generalization of what you're saying. It's learning the scale of different axes.
This specific multiplication.
Multiplication of what?
Here, this.
Multiplication by matrix? Okay. If that relates to scaling of axes, I don't see it, but we could take it offline. You're talking about the basic overparameterization. I don't see how it, because the mapping goes through each matrix entirely, so I don't see how they This is an analysis of what happens, whether that's what it is or not. I guess it's a matter of interpretation. You could take it offline. In any case, for now, what we've seen is that when you take a linear model, replace it by a deep linear network, this is what gradient descent boils down to. And it is some form of preconditioning that promotes movement in directions that the optimization has already taken. Okay? Let's now consider a special case and be a little bit more concrete. Okay? Let's consider the single output case. This is the case where the linear model has a single output. It just maps a vector to a scalar like what we saw in the warm-up. Okay? In this case, the end-to-end update rule looks like this. Okay? This is the end-to-end update rule. Let's ignore the blue. I hope you can see the colors here. So let's ignore the blue and brown parts. We just have gradient descent. Okay? WE at time t plus 1 is equal to WE at time t minus learning rate times the gradient. Okay? Now let's see what these two terms are. Okay? So the first one, the blue, that is the norm of our location in parameter space to the power of something. Okay? And that is some form of adaptive learning rate. Okay? It is a multiplicative factor. It's a scalar. The farther we are from initialization, the larger this factor is going to be. Okay? This is a factor that increases step sizes as optimization progresses. Okay? That's the first element that you see here. The second element is this brown part over here. This is some constant times the projection of the gradient onto the direction of where we are in parameter space. Okay, let's look at this little figure. We started near the origin and then we move in parameter space. We've reached this point. Now, this term here projects the gradient onto this direction, the direction of the point where we are, and stretches that. Okay? So this is some form of an inertia. Okay? It stretches the gradient along the direction that we have already taken. Okay? So we see that in the single output case, when we replace the linear model by a deep linear network and apply gradient descent, what happens behind the scenes is what you see here. The learning rate gets multiplied by a factor that gets larger as you move from the origin. And in addition to that, your gradient gets a boost in the direction that you've already taken. Okay? All right. So, notice that this update rule, okay, this end-to-end weight matrix, moves according to a scheme. The update rule does not have any memory. Okay, I was asked about this before. Okay? There is no information from the past explicitly encoded here. Okay? We are moving, and the step depends only on where we are right now in parameter space, only on WE, and only on the gradient. And now there's a question. Can this optimization scheme be realized as gradient descent over some other objective? Okay, we had our original loss function. We could have applied gradient descent over that. We didn't do that. We used a linear network, and on that we applied gradient descent. That induced some weird update rule. Now we're asking, is this update rule that we got, is that equivalent to taking the original loss and modifying it in some way? Okay? That's called regularization. We usually associate these days regularization with generalization, but the regularization is also something that people use in optimization. They modify their objective to converge faster. And there's a question here of whether this update rule is equivalent to some regularization. Okay? So obviously it depends on the loss, because if the loss is constant and the gradient's always 0, this update rule means that nothing's going to move. And so obviously you can get it by optimizing a constant objective. So that's not an interesting case. But apparently, under a very, very mild assumption, as long as your original loss did not have a critical point at the origin, there exists no function whose gradient is this thing. Okay? There is no function over which gradient descent will give you the effect of depth. Okay? Overparameterizing, adding depth, makes your optimization move in a way that you cannot attain through regularization. Okay? And let's say a few words about how we prove this. Okay, so the basic tool that we use is the fundamental theorem for line integrals. Okay? If I have a vector field, a function from Rn to Rn, I can compute line integrals of this vector field over curves. Okay? And apparently, if this vector field is the gradient of some scalar function, then its line integral over any closed curve is going to vanish. Okay? This is a very, very basic result, hence the name, fundamental. And what we do is the following. We define the vector field to be this expression. That's exactly what we want to show that is not a gradient. We want to show that this thing is not a gradient. This vector field is not a gradient of any function. And we construct a curve over which the line integral of this vector field does not vanish. The curve looks like this. Okay? Never mind all the details. It consists of 2 radial segments and 2 spherical segments. And we explicitly compute bounds on the line integral of our vector field over this curve, a lower bound in particular. We show that this lower bound is positive when the radiuses are small enough. And that means that the vector field contradicts the fundamental theorem for line integrals. Therefore, it cannot be a gradient of anything. Okay? All right, so what did we do up to this point? We had a linear model, replaced it by a deep linear network, applied gradient descent to that. We analyzed what happens behind the scene to the underlying end-to-end model. Okay, we got some update rule, argued that it reflects the dynamics in practice. We interpreted it. We showed that it's not attainable through any regularization. But that does not mean at all, none of these things mean that it's a good thing to do and that it will accelerate optimization. In fact, maybe it slows down optimization, like we saw in Andrew's talk. Okay, so apparently the answer is complicated. And what we're going to do now is go through a very simple illustration on a toy example and try and demonstrate why sometimes it helps and sometimes it doesn't, and then naturally move on to some experiments. Okay? So consider the following training objective. Very, very simple. We just have a 2-dimensional objective. We're optimizing a vector with 2 coordinates. The objective looks like this. Every coordinate's on its own. Okay? And we want to minimize the LP loss of the point W1, W2 when the optimum is Y1, Y2. Gradient descent for this objective looks like this. Okay, nothing special here, this elementary calculus. And if we apply a change of variables, instead of thinking about Wi, we think about the error, its distance from the optimum, delta I, then gradient descent looks like this. Okay? This is just a change of variables. Now, notice that if this term here, if this factor here, if its absolute value is greater than 1, then delta is going to diverge. The learning rate must be chosen such that the absolute value of this thing will be smaller than 1 in all coordinates. Otherwise, some of the coordinates are going to diverge. Okay? So that induces a condition on the learning rate. The learning rate has to be smaller than 2 over the maximum of the initial error to the power of p minus 2. But because we assume that weights are initialized close to 0, this is just 2 over the maximum of y1 and y2. They're absolute values. These are the optimal points that we want to reach, okay, to the power of p minus 2. So what do we have here? This is our simple objective. This is our change of variables. We don't think of wi's, we think of their distance from the optimum. This is gradient descent, and this is the condition that we got for the learning rate. Okay? Now, suppose that the problem is ill-conditioned in the sense that y1 is much bigger than y2. So our error in the first coordinate to begin with is high, and in the second coordinate, it's much, much lower. Okay? So the problem is unbalanced. In this case, if p is greater than 2, and it's very important that p be greater than 2, the learning rate, the condition, the bound, the upper bound on the learning rate is dominated by the first coordinate. Because y1 is very, very large, the learning rate will have to be very, very small. And that would mean that the second coordinate will converge very, very slowly. So if p is greater than 2, and we have some coordinate that starts off with a large error, that forces us to lower the learning rate so that we avoid divergence. And that means that other coordinates are going to pay the price and converge very, very slowly. Okay? That's what happens with gradient descent. On the other hand, with overparameterization, with the overparameterization scheme, the learning rate, as we saw, there's a factor that increases it as optimization progresses. Okay, and so as coordinate 1 converges, the learning rate's going to effectively increase. And that would lead coordinate 2 to converge faster. So in some sense, we are able to start off with a small learning rate, avoid divergence, but as the problematic coordinates are close to their optimum, they induce some kind of, they boost the learning rate, and that allows the other coordinates to converge faster. Okay? And this only happens with p greater than 2. When p is equal to 2, it doesn't matter what your error is, the optimal learning rate is always something fixed. Okay? And we're going to see in the experiments that indeed, when p is equal to 2, and that's the setting that you saw in Andrew's talk, depth does not help. But when it's greater than 2, it can significantly accelerate. Okay? And that's what we're going to see right now. So, LP regression. We are going to consider a very, very simple task where we are just mapping a vector to a scalar in a linear way. And this data set's taken from UCI Machine Learning Repository. I think it's one of the largest regression data sets that we managed to find. A few thousand examples and 128 dimensional instances. The models that we use here are linear nets, okay, mapping a vector to a scalar. And to emphasize the fact that you can get the acceleration effect of depth without paying a computational price, the hidden layers are of size 1 in this case. Every hidden layer is a scalar. Okay, the computational overhead is virtually non-existent. All right, you saw that the end-to-end update rule does not depend on network widths. And so to test this fact, we work with the narrowest network possible. Okay? The hidden layers are of size 1. We also tried wider nets, and they behave exactly the same, just like the theory suggests here. Okay? But to emphasize the fact that the kind of acceleration you get with minimal computational overhead, the results I'm presenting here are with width 1. Okay? So here you can see on the left L2 regression, and you can see that we're optimizing a 1-layer net, that's just the original linear model, versus a 2-layer net, versus a 3-layer net. And indeed, depth slows down pretty slightly, but it still slows down convergence. On the other hand, with an L4 loss, depth gives you very, very significant acceleration. Okay? Overparameterizing with a single scalar moves us from the blue line to the green. Adding another scalar moves us from the green line to the red. Okay? And given these kind of pretty surprising results, there's a natural question of how this implicit acceleration, how does that compare to explicit accelerators? Okay, so we compare a 3-layer net to add a grad and add a delta, and you can see here that it converges much, much faster. Okay? Let's kind of, for a second, stop and think about what's happening here. We had a linear model. We had a convex learning problem. We artificially non-convexified. We introduced extra parameters that turned the problem into non-convex. It now definitely has saddle points. Its objective landscape is seemingly more complicated. And yet, gradient descent on this non-convex objective converges much faster than dedicated acceleration methods for convex analysis, for convex optimization. Yeah, so this is a pretty surprising finding. Yeah. Yes. This is, so here we just took a standard data set. In other experiments, the more ill-conditioned the problem is, the greater the advantage is going to be. But in real-life data, it's typically not well-conditioned. We didn't whiten here or anything like that. Okay, so this is pretty surprising. Okay? This did not happen with all of the acceleration methods we compared overparameterization to. Some were faster. For example, Atom. It did converge faster than over gradient descent over a deep network. But then we tried, without analyzing it or anything, overparameterizing with Adam. Just applying Adam to a linear model versus applying Adam to deep linear networks. And we see that in Adam's case, it also helped. Okay, so this suggests, and this is kind of an empirical observation, that the benefit that comes from overparameterization is something that might not be limited just to gradient descent. There's something that is orthogonal to other sources of acceleration that people use. Okay? Yeah. I didn't, great question. All of the experiments that I'm showing here are for each model, we optimize the learning rate through grid search and choose the best outcome. It's very important. Typically, when you overparameterize, you need to work with smaller learning rates. What we do in this experiment, we have a grid, about 20 values of learning rates for every model. We try out everything, and we present here the fastest, the best results. Okay, we take into account that learning rate was chosen optimally. And the kind of illustration that I showed before suggests that, right? It said you have to choose your learning rate to be small enough, and then you will lose. So we took that into account. Okay. There's a question that naturally arises at this point, and that is, why are you only showing us depth 2 and depth 3 networks? If it indeed accelerates, why not work with a depth million networks? Okay? Where does this thing end? And the answer is something that is pretty apparent in the update rule that we derived, and it's actually something that's well known in deep learning practice also. And it's called the vanishing gradient problem. Look at this term here. It multiplies the learning rate according to the norm of your location in parameter space. If n, the depth, is very, very large, then the end-to-end weight matrix is initialized to a very, very small value. Okay, because each weight matrix is small. You multiply a lot of small things, you get something very small. Okay? And that means that the learning rate when you initialize is effectively attenuated. It's effectively brought down to 0. And that's why you're stuck when you start off. Okay, that's what we saw in Andrew's talk too. Okay, you start off near 0, you're stuck, and then at some point you start converging. The deeper your network's going to be, the more severe the problem's going to be. The longer the time it'll take you to leave that region. Okay? And what people usually do, and what you can see that can be done here too, is just initialize weights to be larger. Okay? They still need to be small enough so that this product of matrices will not explode, but they could be larger. Specifically, identity initialization, that gives rise to what is known as linear residual networks. Okay? Hopefully many of you have heard of ResNets, residual networks. That's something super popular in deep learning practice. Okay? It's skip connections. When I have a feed-forward network, I also connect layer 5 to layer 7 by a direct connection. Okay? And that can be viewed, definitely in the linear case, as just a reparameterization. Instead of working with weight matrix W, I work with identity plus weight matrix W. That's just identical to initializing with identity, and that's it. Okay? And it's called linear ResNets. Okay? Tang Yu Ma and Moritz Hart had worked specifically on this. And we run an experiment with deeper networks than what we've seen before. So we try here 4 layers and 8 layers. In blue here, this is a 1-layer network. That's just the original linear model. In green, that's a 4-layer network, initialized close to 0. You can see that it's stuck until about 70,000 iterations, and then it starts lazily moving along. And in red, that's an 8-layer network, and this is stuck for the entire 100,000 iterations that we ran it for. And when we switched to identity initialization, this problem was effectively eliminated. And you can see here that depth indeed helped. Okay, so 8 layers converge faster than 4, they converge faster than 2. We didn't try taking this to the extreme, but what you see here is that, as in the case of practical deep learning, here too, working with residual networks, identity initialization allows you to overcome many of the difficulties of using depth. And you can still benefit from its acceleration. Sorry?
Are these averages or?
You're asking, why is it so smooth? Because it's not stochastic gradient descent. This is gradient descent. It's deterministic, small learning rate, moves in a very smooth, smooth way. That's an excellent question, which is code for next slide. So we're going to see here a little bit of a more kind of an experiment on a less synthetic case. Okay, so what we did here was just off the shelf, took the convolutional network tutorial for MNIST that's built into TensorFlow. Just took it off the shelf. This is a simple convnet, Linnet, for those that kind of know what that means. 2 convolutional layers, 5 by 5 filters, followed by max pooling layers over 2 by 2 windows. Okay, they all have ReLU activation. The convolutional layers have ReLU activation. That is followed by a hidden layer that maps the roughly 3,000 features to 512, fully connected layer, then ReLU, and then an output layer mapping the 512 neurons to 10-dimensional outputs. Okay? This is trained with stochastic gradient descent, with momentum. So this is not the controlled setting that we ran up to this point. This is kind of just off the shelf, whatever they use. Few details. They also use dropout. Okay? What we wanted to see here is the effect of overparameterization on optimization, again, without changing expressiveness. How did we do this? In a very simple way. We just went to each fully connected layer and added an additional matrix with no nonlinearity in between. Okay, so the first fully connected layer was roughly 3,000 to 512. We added another 512 to 512 matrix. And in the output, we had a 512 to 10 mapping, and we added a 10 by 10 matrix to that. Okay, so I hope you'll agree that this modification does not change expressiveness in any way. Do I? Here, no. Here I initialize actually close to 0, and it's indeed only 2 layers per kind of segment. But no, I didn't even try. The idea of this experiment was to make as little modifications as possible. This is the only thing that we have done. Just took it off the shelf, plugged in these extra 2 matrices. Okay? And the improvement that we got for this specific setting is very, very significant. And this is in log space. Here you can see that things do fluctuate. And with the addition of only 15% in the number of parameters, okay, most of the parameters lie in the fully connected layers, only 50%, the optimization accelerated by orders of magnitude. Okay? So to be kind of fully transparent, we also tried other settings. They all showed acceleration, but this is the most impressive one. So I'm allowing myself to show this one. Yeah.
What's your loss?
What's the loss in this case? Cross entropy.
Cross entropy, and how, is there a way to think about that as it relates
It's a great question.
to previous stuff?
Okay, so what's happening here? This hidden layer, okay, the hidden layer that's fully connected, the objective that it sees is no longer a cross entropy loss, and it changes over time. So it's something that is not immediate. Okay, it's the results that we saw of characterizing which losses lead to acceleration and which don't, they don't fully carry through, because here, in some sense, when you think about this layer, the hidden layer, then the output layer becomes part of the loss, and it changes over time. Okay, so it's not something that we have an analysis for right now. This is an empirical observation. It is something that we are thinking about right now. Okay, not exactly these models, but adapting the analysis to particular nonlinear models. And that does connect to tensors, so maybe next time I will be able to talk about tensors too. Okay. This is one run, but we did run it not a million times, but like, I personally ran it maybe 5 times, and it always ended up like this. This is one run with random initialization. So all of the matrices, the fully connected matrices here were initialized normally with a certain standard deviation, and we use this exact same initialization for the extra matrices. So the batches are chosen randomly, so, but we didn't touch. No, that's cool, but So we did run it a few times, not a million, but a few times. Okay, so this specific thing, I know that it was also reproduced by other people. We had a blog post, uploaded the blog post to Sanjeev's blog, and we got feedback there that the people tried it. I will say, though, that this is not something that's expected to happen in every setting. Okay, we did see an acceleration in every setting we tried, just not that many. It wasn't as significant as it is here. Okay? But this is, you're welcome to try it. Okay? Okay, so let's now conclude. So, as we all know, depth radically changes the objective landscapes. And it makes nice convex problems very not nice and not convex. Okay? And this is something that somehow practically we're able to get by with, but it's not something that we understand very well. And the conventional wisdom is that this makes optimization more difficult. Okay? And I would argue that the objective landscape approach reinforces this conventional wisdom. It will never indicate otherwise. By definition, nothing is as simple as a convex objective when you're only thinking about critical points. What we do here in this work is, for linear networks, we're adding depth as just an overparameterization. We don't add anything in expressiveness. We show that depth induces on gradient descent a particular preconditioning scheme. And that preconditioning scheme, we have a closed form description for it. We have different interpretations. In some sense, it can be seen as a combination of adaptive learning rate and some type of inertia. And we saw that this effect cannot be attained through regularization, okay, which is a standard technique in optimization. And most significantly, it can lead to very significant acceleration. Doesn't happen always. Sometimes it doesn't. With L2 loss, for example, as we saw, it doesn't happen. But in many cases, it does. And the computational overhead that's associated with this acceleration can be negligible. Okay? And a final perspective, this is kind of my personal view, is that approaching deep learning optimization through the lens of non-convex analysis, non-convex optimization, biases us towards worst case scenarios that seem to not happen. Okay? And it appears, we know, for example, that with linear networks, there are saddle points. And yet, when you analyze the behavior of gradient descent, it seems to avoid them. Okay? So the dynamics of the optimization algorithm matter. Okay? And you can't, in my opinion, understand optimization deep learning without taking that into account, and the specific models that you care about. Right? And I believe that this is an approach that might help us develop our understanding, and I'm happy to see that others are taking that stand also. I encourage everyone in the crowd to do so as well. And with that, I'll conclude. So thanks.
Thank you. Great talk. We can open it up to questions now.
Thanks. That was a very nice talk. I wondered if you could reconcile a little bit or comment on the relationship between your results and Andrew's results. Specifically, I thought that he had shown that as you increase depth, you get slower.
Yeah.
And you're saying there's no effect of increasing depth. So what is there a different setup here, or what's the relationship?
Great. So first of all, both of us said that there's no effect in terms of expressiveness. I'm not saying that there's no effect in terms of optimization. So in that sense, it's aligned. The source of the difference is that the loss that Andrew considered is L2, and we consider other losses as well. In the case of L2, we also saw a slowdown. Okay, so it aligns.
Yeah, so I think that is one difference, but I'm still struggling to reconcile. So we did simulations with cross-entropy loss and also saw a slowdown. It was a mild slowdown that you could partially redress by using larger weights and orthogonal initial conditions. So identity initialization is one special case of that. But still, there was definitely overall a slowdown in depth. And I think maybe the difference is actually your initialization was quite large. So you have a 512 by 512 layer, but your initial weights had a variance of 0.1. So if you were considering the weights in that 512 layer, one of those downstream neurons actually does have quite a large norm weight onto it. So I would suspect, not knowing for sure, that might also be the difference. Because at least when we started with genuinely small weights, we saw certainly no speed up from depth. And then just another cautionary note is you can get these extremely deep networks. So I flashed a slide briefly of a 100-layer network training very quickly if you start from large norm weights. That's definitely true. But then it will generalize poorly. So that's another part of the analysis.
Okay, so in terms of generalization, we did not touch on that at all in this work. This is also a linear framework. So there's a question of what exactly generalization means in that sense. On over-determined problems, it probably doesn't mean much. We didn't touch on generalization at all, only on optimization. We did try with initializations of various sizes. The only effect that it had was on the vanishing part in the beginning, indeed, as you say. With cross-entropy loss, it did not lead to acceleration. With L4 loss, for example, I'm pretty certain that if you try it, it will accelerate. But, I think I don't see a contradiction.
So for the special case of small weights and let's say L4 loss, you showed that if you increase the number of layers, you accelerate up to the point in which you run into the vanishing gradient problem. So can you solve for the optimal number of layers in this case? And if not, do you have an intuition about what the solution depends on, which parameters play a role for the optimum?
So you're saying if I don't take the identity initialization path, I stay with small initializations.
Yeah.
I can tell you in practice when it made things much, much slower. That was in the transition from 3 layers to 4. Exact analysis of this, I don't have. I think it depends on the specific structure of the data that induces the L4 loss. But it'd be interesting to think about. In practice, I can tell you that it always happened between 3 layers and 4.
You mentioned that when you compare the performance of depth with Adam algorithm, the improvement is not obvious, or like so how big the gap is? Like what's the difference between these?
Here, what we saw. So it's not okay. Let's see. I think the improvement from 2 to 3 wasn't very significant. The improvement from 1 to 2 was pretty significant here. This is log scale. Okay, so this is a pretty significant improvement. And you can kind of extrapolate. This is just 200,000 iterations. You can extrapolate and continue this way.
Because I think in the formulation, I mean, in that the idea behind Adam is also like adaptively choosing the learning rate combined with adding the momentum. So it seems quite similar with the formula when you analyze overparameterization. So is there any analysis on the kind of equivalence between these two things?
So what you're saying, if I understand correctly, is that Adam on its own includes some kind of adaptive learning rate, which actually operates coordinate-wise, right? It kind of divides by the second moment.
Right.
And it includes a momentum term. And the scheme that we have, for gradient descent, it induces an adaptive learning rate that actually increases the learning rate and some kind of projection. How it behaves exactly on Adam, we don't have an analysis that right now. It's an empirical observation. We could, I'm not sure how, easy it will be, but we could try and analyze exactly what happens in Adam. There are differential equations that model momentum schemes. One could try and do that. That's something that could be done in the future.
Thank you.
Maybe one more question.
Awesome, thanks for that. So I had a question about kind of following actually along what was just asked and relating to when you showed that there was no, closer, this is better. There was no function for which this overall gradient was gradient descent for. Is there a function that this is a Newton step or, a Hessian or something? Could that be the case? can you rule those out using similar methods?
That's a great question. So let's put aside Newton for a second. If you think about momentum, for these algorithms, this question does not make that much sense. For these, it doesn't make that much sense because they hold explicit memory. So obviously, they are not gradient descent over some objective. They hold memory. Right? Specifically for Newton, so we haven't thought of that. I have to think about that. That's an interesting question. If we can modify the objective, putting aside computational questions, just modify the objective so that the steps we get are follow Newton. I have to think about that. It's a good question.
Thank you.
Why don't we thank Nadav one more time, and we can take any other questions at the reception.
Thanks.
And I believe Ahmed and Michael have some closing remarks for the symposium.
Yeah, so thank you all for coming and sticking around all the way till the end. We're going to try to keep this brief because it's late and we could all have more wonderful discussion over snacks and drinks and things. I think we saw a wide variety of perspectives, kind of as Adam alluded to at the beginning, taking different approaches to like what exact constraints you put in the problem such that you can do viable analysis on it. And I think we already started seeing some conversations today on like finding how these things align to get kind of a broader theory. So I think what we really want to, actually before I say more, I also want to thank our sponsors before I forget, the Princeton Center for Statistics and Machine Learning, CSML, thank you, as well as Princeton Neuroscience Institute and the Langfeld Fund at the Princeton Psychology Department. And also the many folks who helped us put this on. With that out of the way, I think what we're interested in kind of having a conversation with you about, kind of starting now and later as well, is where we go from here, right? How do we turn this into the beginning of kind of a potential kind of collaboration, discussion, something between the various groups that are represented here. And so we can open this to the...
If you feel like you have suggestions for us, you can reach out for us if you want to have this discussion now with us or over the dinner, so feel free. Because there is a growing community of people doing theoretical analysis for deep networks, and we want to keep on doing this, bringing not only physicists but also having engineers, computer scientists, and others. So if you have any ideas, you can reach out to us, or if you want to say it now, feel free. Or we can all head to the reception outside. So that's your choice. Anyone have
anyone want to keep us from
burning comments? Anyone have burning comments before we move on? Okay, so we close it, and thank you for sticking for so long, and have fun at the reception.
Thank you.